right? So this is the univalued binary tree question, which is essentially trying to figure out if all nodes in a binary tree have the same value. So let's open up the floor for discussion. All those twos, why? All those threes, why? Are people not talking, or do I have something muted? No, people just
Okay, so the plan that I was like coming up with was obviously we have to traverse through the tree, but we need to keep track. What I wanted to do is that I wanted to keep track of a current, and I wanted to see if the current dot next was equal to that current. If it was, I was trying to see like how I wanted to do it, if I wanted to use like a queue, if I wanted to use like something like that. So what I tried is because I wouldn't do something like binary search. It's not sorted. You know, I know that it's like a it's a tree that every value is the same. So there wouldn't be like the comparison point of like, okay, if this number is bigger than the one, then you know, like I can't do something like that. So I tried using like a queue where it's like, okay, cool. I keep track of a current. If the current dot next is equal to that current, then I'll just keep pushing that into the queue.
Why do you keep saying
If
current
not,
dot next?
oh, I was so I was keeping track of this. I when I was using like a while loop, and I was trying to keep track of the node that I was like starting off with, and I was trying to search through the left and the right node that it would be on.
Okay.
So it
Yeah.
would be if the current dot left, sorry, not next. If the current dot left is equal to that current node, then I'll push that into the queue. If the current dot right was equal to that current node, I'd push that into the queue. And if it broke out of that loop, or like say if we got through, couldn't, you know, and we found something else, and I'd like return false or something, else I'd return true. So I was just trying to write that out and see if I can get that to work. I was still writing it out. So
Cool. So, and what kind of traversal is that?
this was a, I'm trying to find the name. This was a breadth first search
Or,
traversal.
yeah, very cool. Yeah, that seems like a decent approach for sure.
Yeah.
Uh, what did other people think? What were their approaches? What went well? What didn't go well? Don't be shy. Come on. We're on the internet. It's anonymous. Brutus pretty similar to Marvin. Yeah, Deja same approach. Okay. In the nonverbal feedback feature, I guess, give me a yes or a no if your instinct was to do a breadth first search. Curious. Okay. Got a bunch of people not voting, but okay. Of those that are into it. Okay. Yeah, so pretty mixed. So then the nose. So from the nose, does that mean you guys tried to do, or you guys were trying to do a depth first search, or were you guys going a different direction? That's
I
good.
was thinking of depth first
Yeah.
because maybe like say for example like the head node was the starting node was a different node than the children, but all the children were the same. So
Okay.
I was thinking to do the depth for search to get that value, that children value first, to see if that value comes up anywhere else throughout the search.
Okay. That's cool. Makes sense. All right, well, let's start going over it a bit. I'll share my screen. So, this problem, it doesn't really matter if you wanted to do breadth first search or depth first search. You should be able to solve them both ways, ideally, because it's not like we're looking for closest node or something. I mean, even then, right? I personally probably would solve it breadth first search, but there's nothing wrong with depth first search. Right, so we got to look and we see this one's going to give us true because in fact all the nodes are the same. This one's giving us false because we have this 5. So if we're doing a breadth for, we'll start with a breadth first search. So let's try with the BFS kind of solution. Right, so for breadth first search, as Marvin talked about, right, we're going to need some kind of queue. So I'm just going to say let queue, and I'm going to stick my root in there. Now, on the off chance that we're not given a root, I guess we can deal with that then, but that would be a good clarifying question. Like, will we ever not be given a root? So like, if there is no root, is that a unival tree? I don't know. That's up to your interviewer. So I'm just gonna not put anything in there for now. So maybe we can get by without it. So we also need to have something like, we have to check if every node is the same. So if we have a root, we have a starting value, essentially. We have this one value that we can compare every value to, because if they're not all the same to the root, we know that it's not a univalue tree. Does that make sense? Does that logic, does that step make sense?
Yeah, but can you have a univalued tree that has a wait? Oh no, never mind.
Because every
Node, yeah, I just read it again.
right, since every node, right, we could have subtrees. That would be a very interesting problem. If that's what you're kind of leaning towards this year, that would amp up the difficulty, I think, a bit, which is like return every univalued subtree. That would be very interesting. Then I'd probably be more inclined to do depth first search, to be honest. Okay, so we've got our starting node value. So let's just say like let compare value and just give that a root.val. Right, so we'll just compare every single value as we iterate through the tree to the compare value. And if it's not the same, just return false. If we make it through the whole tree, we return true. So then we can write our breadth first search. So we'll check while our queue.length is greater than 0. Oops, I jumped to the top somehow. Sorry about that. Or just while queue.length, but I'm just going to be more explicit. We can go ahead and grab our node by shifting out of our queue. This should give us, in the first iteration, that will give us the root. And we can do our check. So hey, if node.value does not equal our compare value, what would we want to do?
Return false. Return false.
Yeah, right. If it's not the same, we got to return false, because this means they're not all the same. Otherwise, we can go ahead and push its children into the queue. So we can say if queue, if node.left. So if there's a left node, let's go ahead and push node.left. And we'll do the same thing for the right. So if it has a right child, we'll say q.push node.right. And that's it. That should iterate through the whole thing. And if we make it through, we'll just return true at the end. So I know I'm not doing curly braces because these are just read these as one line things. So if this, do that, if this, do that. So all this does is we take this value in the beginning that we want to check everything against. We set up a queue. We say while this queue's got length, we're gonna take a current node, compare that current node to our compare value. If they're not the same, we're returning false. Otherwise, we just push whichever children it has into the queue so that we can evaluate those next. We make it all the way through. We return true. Let's see if something like this
Hey, Corey.
work. Yes.
What's the difference between the one-liners where you have the return without the return line, like for example, line 19
So
compared to line 20?
Oh yeah, this returns.
No,
right?
I mean, how come you didn't write return for 20 and 21? Or no, because that would end the function.
Yeah, these don't return. These
Okay.
are just logic that would go inside of the if block.
Okay.
Yeah. But if you're just gonna write it on one line, you don't really need the parentheses, not the curly braces. You can. It just depends on what's cleaner to you. To me, this is cleaner, but I can put them in curly braces if you want.
No, that's okay.
Okay. So we try this out, and looks like it works. All right, so this is a viable solution. Let's try it again. I'll just comment this out, and let's go for DFS, which is a little bit, I think, harder. Is Unival tree, but not too hard. We'll see. Okay, so DFS. Before we move on though, for this BFS one, what's our time complexity here?
Linear.
Linear. I heard somebody whisper linear too.
That was me.
That's you, Henry, right?
Yeah.
And what about our space complexity?
Also linear?
Yeah, I think space complexity is a little, it's just whatever the width of the tree is, right? Because that's the most we'll ever have to hold at once in the array, in this queue. This size of this, since this goes layer by layer, is pretty dependent on how many levels we have. So each level, I know there's a math thing to it, because your height, each height potentially doubles. So it's probably like, yeah, I think it's like the height of the tree is. So I think.
Hey,
So,
Corey, before
time?
we move on,
Yes.
I have a question.
Okay,
Or
just
not a
give me just
question.
one
Yeah.
second. So time should be linear, and space should be O of H, which is height. Because if we look at our trees, right, if it was only a height of 1, there's 1 node. Height of 2, 2 nodes. Height of 3, well, this could have been up to 4 nodes. I'm just gonna call this width. I know there's a calculation in there. I'm not good enough with math. But it's whatever the width of the tree would be the space. Yeah, Ashia, what was your question?
So, I tried submitting the code.
Okay.
Wait, never mind. I think I had an error.
All right.
Okay.
Did you get it?
Am I spelling right? No, I'm not. I can't spell.
Okay. That's all right. All right, so let's keep going then for our DFS. We will you could do the same kind of thing, right? We need this value to compare. So let's say let compare value, and we'll just set that to root dot val. So everything can be checked against this. And then let's go ahead and write a DFS. So I'm just going to write DFS. All this is going to do is it's going to take in a node. It's going, if there's a node or if there's not a node. So if there's no node, that means I'm calling DFS on an empty tree. I'm just going to return true. Otherwise, I have just a little bit of logic, right? I need to check that my current node is equal to our compare value. So I'll say return compare value is equal to our node.value. But I also need to make sure that this is true for the left side as well as the right side. So I'm also going to call DFS. So I'm going to say and our DFS on node.left. Oops. And this is true for our DFS of our node dot right. And then at the end, we'll just go ahead and return DFS, and we'll pass in our fruit. And this should work as well, right? So we've got our compare, our value that we're going to check every single node against, and we initiate with the function call to our DFS with our root. So that's our very first node in the tree. And we check, hey, if there's no node, return true. And I'm doing that because I'm not calling to check if the node has a left or right. So sometimes a null value will be passed in here, and I just don't want that to break things, because just because something's null doesn't mean it's not the rest point true. So that's why we're doing this check. So if there's not really a node passed in, we're going to return true. Otherwise, we want to check, is the current node that we're on equivalent to our compare value? Okay. And is that true for its children, for both its left as well as its right? And this is a recursive function, right? So it's going to call this for every node in the tree. So let's go ahead and check this one. So we'll start off just by running the code and submit it. And this will also work. Any questions on this one? What's our time complexity here? A little bit more back and forth today. Come on. I feel like I'm pulling teeth. It's all right. It's okay to talk.
Exponential.
Exponential. Okay. How come?
Because it's recursive.
Okay. So a recursive function doesn't actually mean that it's exponential. That's only if we didn't have good recursive practices like memoization and things. This is really just linear, because it's only going through each node. I think, unless I'm wrong, I think it's, hang on, this is a little tricky. I'm pretty sure this is just linear, because we're making this call for every node. You know what?
I think it is linear, because it's like it's going through. Yeah, it's making the call for each of the nodes for like both left and right. So I think it is linear.
Yeah, but
does it have to like traverse all the way down first and find the point, and then traverse all the way back up?
It is going to go down, yeah, all the way down to the left, and then it will come back up. But because we're never calling the method on the same node multiple times, I'm pretty sure this is just linear because we're just touching every single node once. Yeah, we'll keep going down the left until that settles, and then they'll start going down the rights of those. So in this example here, we would be going, is this true? Yeah, and then we would go to the left, which would be checking if this is true. Then it would call to the left, and then we'd go here, and then it would come to here, and then we would finally go to here, and then it would check its left, doesn't have one, and then it would go down to its right. It's a good clarification, Doug. As far as space complexity goes for this, I think this is the honestly, I'm not 100% sure. I think it's kind of the same as stack frames for each node. So not 100% sure. I know that's not a great answer, but I'm not gonna guess and get it wrong. But open to people's ideas, and if somebody has a good reason for what they think for their space, like, talk about it, tell us about it. But any questions on actually the logic of either of these? All right, then I guess that's it. Let's stop the share, stop the recording.